I would like to introduce Tony Adamson from NXP. He's going to talk about the migration to CAN-FD, so please enjoy.
Okay, thanks very much. Can you hear me at the back? Okay, sounds like it's okay, good. So at the last conference, Holger introduced this slot as the slot for the youngest person to give a bit of energy. That last privilege was for Artur, now the privilege falls to me, so I guess I should be flattered that I'm still falling into the young age category. Thank you, Holger. I wanted to speak a little bit today on some of the trends that we see with migrating towards CAN-FD. I've got quite a lot of information I want to get through. I'm not going to be covering directly everything that I put in my paper. That's sort of already available in the proceedings. I will reference that some way, but I also want to go a little bit further than that today and give some new insights that we have relevant. So just by way of a quick review, I'm speaking here about CAN-FD in automotive. That's my core business. That's what my main focus is on. And the connected vehicle is really going through quite a revolution. We see that basically becoming much more of a connected device. It's exposed to things on the roadside, from mobile devices and so on. And this is having big implications in the way that data is being managed in the car. If we're looking also to the path towards self-driving vehicles, autonomous driving, there's more data that's going to be coming into the car, and that needs to be managed in different ways. So that's why we really say secure and connected self-driving vehicles. Security and connectivity will be key drivers. And I think for the in-vehicle networking, it's really going to be about bandwidth or speed and security. How I go from the networks of today to the networks of the future. The networks of today are typically categorized by mostly being dominated by classical CAN, typically no security, simple architectures. Different OEMs may be somewhere on this continuum at different places, by the way. But typically, the system is going to be quite squeezed in terms of bandwidth and EMC and so on. And over on the right, if we look 10 years ahead to the self-driving vehicle, we're going to have what we think anyway is two main technologies, which will be CAN-FD and automotive Ethernet dominating the communication space. There will definitely be more, so also things on the body network side, and also maybe things like hyper-gigabit and these kind of new technologies where it's a complete open, blank piece of paper at the moment in terms of what will end up there. Security is going to go hand in hand, and performance requirements in terms of ENC and these kind of things are also going to increase. And we also think that the actual end nodes themselves, the integration level that we have on the end nodes will go from being quite simple devices to much more complex integrated devices, what we call the smart node. And going from where we are today to get to that vision, we think there's quite some challenges as an OEM that you need to overcome. Major investments in a network re-architecture. That's a big, expensive change that needs to happen. And strong security is not even possible really on classical CAN as it is today. So that's also motivating the change for some people to go to CAN-FD. But the rollout of CAN-FD is also being hindered by things like ringing, by the EMC performance, and also the lack of CAN-FD as well as secure MCUs is also overall slowing the process and adoption down. So really our strategy, and I'm responsible for our standalone transceiver, so we're part of the in-vehicle networking group. Our mission is really to try and give opportunities and options towards OEMs about how they can actually manage this transition in the easiest way possible and seeing how the CAN transceiver can play a role. And that task is typically one that NXP has always played. We've also been playing in CAN for more than 20 years. Our first CAN transceiver was launched in 1993. Sorry, the text on some of these slides will be a bit small. I was hoping for a bit more of a bigger projection, sorry, Holger. But I think even for the last 20 years, we've always continued to play the innovator role. We've tried to look for new opportunities, whether it's in fault-tolerant CAN, partial networking, automotive Ethernet, whatever. There's been time and time again where we've tried to really drive value into the market. We've co-invented most of the IVN solutions, and as a result, we remain the market leader. Our competition do a very good job of keeping us honest, but we're working very hard to basically maintain that position. For CAN-FD itself, I think this slide in terms of technical content is all well known. Just to give an insight into what NXP has been working on, we've been the technical editor of the new ISO specification, the ISO 11898-2 2016 revision, we've been guaranteeing our transceivers, and now the transceivers that you buy from NXP are pretty much all guaranteed at 5 megabit according to bit timing defined in that standard. Even at 2003, we were announcing the Mantis transceivers, which were able to do 2 megabit EMC, so already preempting these new requirements. And we also do a lot of simulation work with OEMs directly, which has given us a lot of insights into actually how the network, our transceivers are being used in networks, and networks are being built, and the kind of challenges that OEMs are facing. So I have to show this slide, which is my portfolio. And basically, you see pretty much everywhere there's 5 megabit guaranteed. The only, I think the one notable point to also mention, and I believe my colleague from Infineon will also be discussing on the wake-up timer, if I interpret your title correctly, that's a new requirement that's also been coming out in addition to make sure that we're having reliable wake-ups happening at CAN-FD. That's also a function we will support. Our first one, the 1044G/3, that's our transceiver where we were able to get that requirement on. Pretty much that's just work. I'll leave it to my colleague to explain what it is and the details of it, but we will also do in our next generation. So where I really wanted to spend the majority of my talk on today was actually about how you actually go about building a CAN-FD network and doing that in a reliable way. And really I want to focus on one key topic, and that's about ringing, which is really by far the most important challenge. Dr. Islinger, who is chairing the session and introduced, has really, I think I have to also give a big kudos to Denso Semiconductor. They've really actually raised the profile of this issue, and they've been promoting a ringing suppression circuit. And I think I really have to give a lot of thanks and recognition to the work that Denso's been doing, and actually promoting and raising awareness of this challenge within the industry. Just by way of review, the ringing is the biggest issue when coming from the dominant transition or dominant bit to a recessive bit. And that is basically then creating, and I seem to have a problem with my laptop. Okay, let's see how we go. And that's basically creating some ringing and reflections in the recessive bit. And that can cause false triggering of the RxD to actually register on a dominant when I actually am at a recessive level. Now, normally for classical CAN, that's fine because I have 2 microseconds bit time, everything is dissipating, and there's no problem. I can reliably read. I have an accurate sample point by the end. The problem comes when I shrink that bit time, and I now start to sample what my bit is. And if I'm doing that at 2 megabit per second, I've only got 500 nanoseconds, and the chances are I'm going to be sampling within the ringing itself. And it's really pot luck as to whether I'm going to get that reliably or not. And that can be differing on different nodes and so on. So really, at this point, communication errors are going to abound. And that really becomes a block on how far you can actually roll out CAN-FD. What I cover in my paper is also some assessment criteria that we've been working with and developing with OEMs on actually how you can do network simulation to ensure that ringing is not going to be an issue. And if you look into the paper, you'll see it's not just at the sample point you need to factor in, because really you have the worst case of 5 dominant bits followed by a recessive. And you can have to add up all your tolerances and drifting that you may experience in your network over that time. And that actually brings you out to a sample point closer to 48% of your bit time. So you really have to make sure that quite early on in your bit, you have clean ringing and you're able to, or clean signal, free from ringing. So until at the moment, there's not really much we can do about the ringing other than just try and manage it within the networks. And that typically comes from compromising on the topologies that are used. So there's a big focus now on linear topologies, or daisy chain topologies are also known as. And I give an example here where you go from node to node and just daisy chaining around that one. So you're having very, very short stubs, which are the primary culprit for causing this ringing. The problem with that is I've got extra cabling when I don't really need it. That's going to be costing me additional cable. It's going to be creating weight in my vehicle I don't need. And also we get feedback from OEMs, things like production testing can't happen if all the ECUs aren't mounted. So they have to change the way they're managing their production flow. Or if they have an optional ECU, then they need to have a different kind of wiring harness. So it's creating all kinds of additional complexities in their supply chain. We also see, and I cover this also in my paper, there are actual limitations. Unfortunately, it's not really coming up here very well. But in this example here, when coming down to a recessive signal, if you're putting up multiple nodes in a daisy chain, the 47 picofarad capacitance is actually creating a capacitive load in your network, which is preventing that recessive signal from coming down to 0 on time. And that can actually create, and it's difficult to a bit see on this projector, but it's creating a lot of RxD jittering, even when there's actually no ringing taking place. So it also has its limitations in some way. The other option is you can, of course, segment your network into different branches, or you can reduce your bit rate, both of which we know other OEMs are also working on. But these aren't really this direction we want to go with. So now I want to give a bit of a nod in the direction of Denso Semiconductor and talk about what they've been producing, which is on ringing suppression. So their concept is I can replace my standard CAN transceiver with a ringing suppression transceiver without making any other changes in my application. And I can accelerate the feasible bit rate in the network. This is their concept. Mr. Islinger, Dr. Islinger, I hope you don't mind. I've given reference to your paper. This is from their paper 2 years ago. But it's a very nice example of what you're doing, where basically their solution is listening on the bus, simply, and waiting for a dominant to recessive transition, and then activating a switch, which is then making the impedance on that 120 ohms perfectly. And with that, they are suppressing the ringing. They're matching the impedance on the bus, and then they're suppressing the ringing. And they're showing pretty good results. And I think that's now been put forward in the specification within the CAA 601-4. And we've also been reviewing on that and giving comment as well. Talking about ringing and ringing suppression, we also get, I think, more market requirements about CAN-FD going forward. And I've kind of also tried to summarize that we've sort of got from the market. I think any solution really needs to be fully robust and really predictable. What I'm designing on my bench, what I put into my vehicle, what I'm simulating in my network, and what ends up going in production, every step of that way needs to be predictable, understandable, measurable, quantifiable, and reliable. And now, the reason I mention that, of course, is because now we are going to be doing some active manipulation of the bus signals. And so we need to make sure that that's happening in a way which is understandable and predictable in terms of behavior. Error management must still work. So if I'm now pulling something towards a recessive signal, I still have the case where the error frame can be sent during the data phase, and I need to make sure that that error management is being handled as well. So I need to ensure that the dominant transceiver can still send a dominant error frame without any problem. 5 megabit really is, I think, a clear market requirement as well that we hear coming back time and time again. I think if we're not able to deliver on 5 megabit in good-sized topologies, we're going to fall short of, I think, where ultimately CAN-FD could fulfill. And there's going to be new technologies like even maybe 10 megabit Ethernet, which is going to challenge for this space. So the cost advantages have been spoken about this morning, and I think really it's our view that if we want to come up with really the big success for CAN-FD, we need to show a solution which is having a path towards 5 megabit as well. No topology restrictions, so that it's fully usable anywhere and everywhere. No single point of failure, so also if an ECU is suddenly going bus off, and that is providing ring suppression, we need to make sure that that network is still able to communicate reliably. So we need to make sure, again, linking to that, now influencing on the bus signals, that we're doing that in a solid, robust way. And more of a hygiene factor, but also meeting on the EMC limits. So I wanted to give a bit of a comment now on the current specification as we have it. And the reason I want to do that is I'm not now trying to trash the 601-4 specification, but we wanted to also bring in some new insights into here, so how we think that this might look like in the future. And we want to really start engaging now with that standardization group. And so that's what I want to share here today. I think the key thing that we need to make sure is as I say, that we have predictability. And they propose triggering off the bus. So it's looking and trying to interpret what is exactly happening. But we know that the bus is fundamentally unreliable in terms of a medium. It's noisy, it's got glitches on it, it's got EMC. So there's quite a challenge to make sure that what we're detecting as a dominant to recessive transition is actually data and not some kind of EMC or noise injection. Let me give you an example of this. Oh, okay, this is not really coming out so well. But this is showing basically an EMC being injected into my network. So if I'm having basically, this is my differential signal that I would see here. And in my dominant bits, due to asymmetries that I have in my cable, I will get EMC noise being converted towards a differential signal. And as that EMC is being increased, or if my asymmetries are growing, you can't really see it here, but you actually see the threshold limit for the ringing suppression circuit is being tripped. So that means that EMC, which will be happening in the vehicle for quite some time, could be triggering on the current proposal. And that's, I think, not something that we want to happen. Likewise, if I go back to this example on the plateau effect, the minimum specification, or the minimum voltage specification at the moment is 0 volts, but we can't always guarantee that that is going to be met. This plateau effect is actually prolonging that triggering happening later on in the bit time. So if I'm now suppressing my ringing, the effect that will happen is actually start also eating into my next dominant bit, which is the synchronization point for my network. So then I'm going to have big synchronization issues potentially if that's not working reliably. So we need to really make sure that, like I say, we have a predictable system going on that's able to apply ringing suppression in a good way. There's been actually a refinement of the solution, and I think Denso's put some very creative proposals in there. They've been looking at different ways of applying filtering. I think we're not quite there yet, but I really appreciate that insight that they've been giving. So, as I say, this is not me now trashing Denso Semiconductor in front of everyone, but I think it's just to raise some of our concerns that we have when looking towards this. I think in recognition of the value of the work that's being done. And the second one, I think, is the key requirement is speed. We need to have a clear pathway to 5 megabits. Now, what do I mean by that? Because you can actually get a point-to-point network working at 5 megabits, right? So I don't even need ringing suppression to get 5 megabits. So, but structurally, the proposal by triggering off the bus is, for us, in our opinion, too slow. And I'm going to explain what I mean by that in the next slides. But by the fact that I can actually already do 5 megabit on a point-to-point connection means we also need to start thinking about a kind of what we call a figure of merit. It's something already that me and my colleagues are thinking about, how we can define what topology should we be designing for with a ringing suppression solution. What kind of power of ringing suppression is needed in order to be certified as being sufficient for the industry. We need to kind of put some quantifiable measure on that at the moment. And at the moment, we just don't have any real numbers around that one. So I'm going to go a bit into hardcore timing diagrams. Please bear with me. I know you've had the lunch. Your blood is going to your stomach and digesting, but please stay with me. What I'm showing here is basically about why we think that the current proposal is going to be too slow. So on the top, you see the TXT signal, and here you see the differential bus. Unfortunately, due to the resolution, things are being corrupted, but basically what I'm showing here, we have our nominal sample point, our corrected sample point. So kind of by this point, we need to have ringing looking good and under control. I've taken the values from the specification that's being proposed and basically put here the RSC suppression time. So this is the RSC activation. Here it's coming on. This is my start time that's defined, and then my suppression time. So here we have a bit of a delay that we see. And I've started this delay on the point where the impedance on the bus is going from the dominant to recessive. Okay, so dominant, it's at 30 ohms, and the recessive is going up to 50 kilo ohms. And at some point, it's going to match the 120 ohms that's the impedance on the bus. If I'm losing some people, I really do apologize, but hopefully some of you are still able to understand this. We're getting very technical now. And this is really, for us, the danger area, this area where it goes above the 120 ohms, because at that point, my reflection coefficient is going to tend towards 1. Okay, so that means that basically my impedance is going to be high enough where I'm going to be generating reflections going off. Okay, one person is nodding, so at least I've got one person in the room. What I mean by reflection coefficient is basically how much reflections are being generated out. Okay, so I calculate that by the impedance of my transmitter minus my impedance on the bus divided by my impedance on the transmitter plus. So I do the delta basically. And you see when 50,000 versus 120 ohms, the 50,000 is dominating. So pretty much this is tending towards 1. Whereas on the dominant level, I've got 30 ohms minus 120 ohms divided by the 30 plus 120. So that's coming out at 0.6. That's already given me a damping effect already. So in this danger area, as I say, that's why I'm tending towards 1. So that means this is going to be where a lot of reflections are going to be sent out back into the network. That's the problem that I have. Now at 2 megabit, this is probably going to work okay, because you see, even at my corrected sample point here, I've got a good amount of time to do the ringing suppression, and that's what we see. We see that the results from Denso are showing that the suppression is working still reliably. The problem is when I come to 5 megabits and I pull everything in, I've actually got very, very limited time, basically here, in order to get the ringing under control. And that's where I think the problem is lying. Now let me try and explain that maybe again, if I can. I've lost my mouse. Okay. Sorry for that. Okay. Let me try and now visualize this. So if you're not really into your numbers, let me just try and visualize it. Another way of explaining the same thing, I've basically created a simulation here. Well, in fact, my colleague Clemens did. Where I have one node here sending some reflections wave going in, and node 3 is going to be receiving that. Node 2, the top 2A and the bottom 2B, they are the perfectly terminated nodes. So they've got the termination resistors on. And so they are basically, we model that basically as two in parallel, so 60 ohm resistor in the middle. What we're going to simulate is just an ideal transmission line, so there's not going to be any dampening, and infinitely fast edges. So the normal ringing that you see with the sine wave, you won't see. It's just going to be straight lines. It's not really valid so for sort of taking accurate measurements, but it's just to demonstrate the concept. And what I want to do is just show you what happens when we start with a delay and then we start reducing that delay. Okay? So this is, again, we started now with this, I've rounded up to 70 nanoseconds here. That was a delay. That's the red zone that basically we have before we're applying the ringing suppression now at 5 megabit per second. And you can see here at the sample point, which is this line here, I'm above the minimum threshold, which is the black line. So I've got ringing here at the moment. If I now start pulling that one in and reducing that delay time, so I'm getting faster and faster and faster, you see the ringing is less and less in the dead time. And so the ringing is propagating less until ultimately when there's no delay at all, I have the best performance. Okay? So coming back to that timing diagram, what I'm saying is I'm now just reducing that red time and I'm pulling in the activation of the RSC as fast as possible. And what this is doing is it's buying margin in your network. And we know, for example, due to the CAN-FD bit timing, where now 5 megabit bit timing tolerances are being requested for 2 megabit operation, OEMs like margin. So we think this is really the way to go to improve and get towards 5 megabit per second. So, okay, so how do we do that? We have a bit of a conflict, unfortunately, because we want to get a fast-acting ringing suppression circuit, but we're receiving off the bus, so we need to do filtering, which takes time. So I have a problem here. And I think that's our overall comment on the current direction that the specification is going. If you're going to introduce filtering to make sure that it's reliable, you're going to run into trouble with the 5 megabit, and we need to do both. So in fact, our solution is that you need to do it TXT-based. TXT is going to be the fully predictable signal, and it's going to provide you the fastest reaction time. Okay? Because I can even start reacting on that TXT before the signal is hitting the bus. I can already start influencing that way ahead. So that's basically our proposal that we need to make towards it. And it's also based on the insight that applying ringing suppression at the transmitting node is already enough. And so the last part of my presentation is just to give you some examples of that, if my laptop would work. Come on, dear. You can do it. There we go. So again, I've borrowed your diagram, but this is the CIA topology that was created, I think, by VW as an example of really a worst-case network. And we've just taken basically the TXT from ECU1, and then we're looking at RxD from 1, 2, and 11. We would also look at 7, but we don't have a scope with 4 inputs in, so we're only with 4 inputs, so that's what stops us. So if I look at, I'm just using an example here, so I'm transmitting it at ECU1. With standard CAN transceivers, I'm now measuring, and I'm seeing ringing coming back at the RxD signals on ECU1 and 2. If I now put in the ringing suppression circuit from NXP, I'm getting a clean signal on RxD. Likewise, if I do from ECU2, I get a similar signal on the receiver, and then those are being cleaned up. Likewise at ECU 11, I'm seeing that the GIS are coming back here now on the ECU 11 on the RxD, and then with NXP solution, that's all clear. And we've tested this in a lot of topologies, so we've got pretty good data points that this works reliably. So that's my message, basically. I'd like to introduce you to Falcon, which is going to be our code name for this part. I get the glory of having beautiful clip art to put on here. We're busy developing this solution. It's going to be TXT-based, so it's going to be fully predictable. We will be also offering both 2 and 5 megabit versions. We have samples available today, so if you would like to evaluate this technology, you can in your own networks. And we are working towards a release next year. And then the last statement, I think, looking towards digitization, is that also we need to really think about this figure of merit. We need to start aiming as an industry towards when we think about ringing suppression in the standard, about what that will mean and how we can evaluate the different alternatives. So thank you very much. That's my presentation. Yeah.
So thanks, Tony, for giving us a lecture on ring suppression.
Normally your job.
Normally my job, yes. Questions from your side? Yes, Magnus.
Could you say how you have achieved this TX-based ring suppression and give us some more detail? What is the consequence on the transceiver chips, what you have done, and how it looks, makes it more expensive, those transceiver chips, and what is the technique behind that?
Not at the moment, and not in this forum. But I think in due course we can give away more information about that. I think again, we want to. I think your organization, CA, is working on the standardization, and I think we would like to bring this towards a common solution in the industry. So I think it's not in anyone's interest that we're now creating multiple solutions that are going to be competing. So as we're going into that discussion, of course, we will be giving away more information as we go forward.
Other questions? Okay, so then, thanks a lot.
Thank you.